Good evening. I'm Walter Craig. I'm the director of the Fields Institute, and I'd like to extend to you a very great welcome to everyone for the public opening of the Fields Medal Symposium 2014. This year's symposium is, well, you can read it on the sign. It's The Many Facets of Entropy. Well, kinetic theory, optimal transport geometry. It's focused on the research and the research interests of Cédric Villani, who's a Fields Medalist 2010. This is the third Fields Medal Symposium in existence, and we expect this to be a tradition that extends on to infinity. So every 4 years, there's a Fields Medal ceremony at the ICM, the International Congress of Mathematicians. And normally there are 2 to 4, we hope 4 Fields medalists awarded each time. So that fits nicely into a 4-year cycle of 1 symposium per year held at the Fields Institute on the University of Toronto campus and in Toronto. This evening, we have planned a public lecture by Cédric Villani, preceded by several presentations by special invited guests. But before we start, I'd like to say a few words about the Fields Medal and the Fields Medal Symposium itself. So the Fields Medal is recognized basically universally as the most prestigious international prize in mathematics. It's awarded by the International, the IMU, the International Mathematics Union, every 4 years. And the first one was awarded in 1936, I believe, and so far there have been 56 Fields medalists in total. It's often said that the Fields Medal is the mathematics Nobel Prize because Nobel did not see to award, to endow a prize in mathematics, but in other subjects such as physics, chemistry, medicine, etc. Just to compare, there have been over history some roughly 200 Nobel Prizes in physics compared to 50-some in mathematics, so I think of that as the denominator. This is in terms of prestige, you might say. But I'm a mathematician, so you have to take that with a little salt, a little grain of salt. So being the Nobel Prize in mathematics, I have to say that it differs in several significant ways from the Nobel Prize itself. One is this interesting constraint. I think it's not ever written, but it's certainly the tradition that is awarded to recipients under the age of 40 in order to encourage further achievement on the part of the recipient. So this means that someone in the early or mid part of their career, where they have reached achievements but they have plenty of time for further achievement, is given an award, rather than what happens fairly often in a Nobel Prize, a great achievement recognized at the end of a career. There's another quaint habit that is part of the Fields Medal tradition, which is the Fields medalists are announced only at the International Congress of Mathematicians every 4 years, and their names are not released ahead of time. Well, last time there was a hack, and they were by accident released a couple of hours beforehand, and most of us knew, and it passed around. But that was a mistake, and I think security is going to be greater on the website from now on. But it means that there is not a symposium or at the award ceremony, because if you arranged a symposium, then it would be absolutely obvious who you're arranging a symposium for. So there are not symposia in honor and on the subject matter of the Fields medalist work at the ICM itself. This is in contrast to the Nobel Prize, where there's no Nobel Symposium, or the Abel Prize, which is a relatively new major prize in mathematics, which has an Abel Symposium associated with it. So the Fields Medal Symposia are in part to make up for this lack. Of course, with a necessary delay after the award of the Fields Medal, and because of this 4-year cycle, it can be some years delay, but all the better for being well prepared. The symposia are not award ceremonies. They are scientific meetings which bring together top international researchers in the medalist research area in order to take on new frontiers, communicate the cutting-edge research, and basically to consult. They're also aimed to increase public awareness of the Fields Medal. Hence, our opening today, which is going to feature a public lecture and also some comments by very, very well-known and public figures. They also are to highlight scientific impact of the medalists' work, and also the impact of the medalists' work and also of mathematics on society. So that's something I would like people to reflect upon. Furthermore, a Nobel Prize, an Abel Prize, the Shaw Prize, other prizes are very well endowed as compared to the Fields Medal. I'd like to make it clear that the Fields Medal has a very intimate tie with Canada and indeed with Toronto, since Fields was born in Hamilton. He's a Canadian and was a professor for most of his career at the University of Toronto. The endowment's held by the University of Toronto. The medals are stamped in Canada. It might be in Winnipeg, I'm not absolutely sure, but at some mint, and then in any case, the stamp, which is the Archimedes, etc., with the Greek and the Latin, that's held in Canada. And it's this funny quirk that somebody from Canada, it happened to be Robert McCann this time, carries these 4 medals in their backpack to, this time, Korea, in order to hand them over to be awarded to the medalist. Seems to be a lack of security on this, if anybody knew, but since it's a secret, then it doesn't really matter. But another thing I want to say is that endowment came out of a professor's salary. This is John Charles Fields himself, and so it is very modest. So it's actually 2 orders of magnitude off of, say, what a Nobel Prize would win when that's awarded. So a third purpose of the Fields Medal Symposium is to offer the honored medalist a significant honorarium. Okay, this is still modest by Nobel standards, and it's still 2 orders of magnitude off, but nonetheless, it's useful, and maybe we can build this over time. Finally, it's to raise the public profile of the Fields Medal and the Fields medalist, and indeed mathematics as a whole, for its impact on science and on society. Finally, the purpose of the Fields Medal Symposium is to inspire scientific activity in Canada, in part by raising awareness of the fact that those connections with the Fields Medal and Canada and Toronto and Hamilton and the University of Toronto itself. By the way, you probably, if you pass through the lobby, we have a replica of the Fields Medal. It's minted in silver and gold plated, so it doesn't. So Cédric said it's not as heavy as mine, but it's nonetheless, it looks the same, and it's just on display, so you can actually see it. And it's in somebody's pocket right now because we're all here and we're not out there at the table. Okay, the Fields Medal Symposium are organized by the Fields Institute, which is down the way located down the way on College Street. It's a creation, actually, of Edward Beerstone, who was the former director of the Fields Institute, and it's made possible in part by the agreement with the International Mathematicians Union that this is an activity that is positive and sanctioned by them. So it's in concert with the IMU. It's certainly made possible by funding, very generous public funding from the Ontario Ministry of Training, Colleges and Universities, and by NSERC. That's funding is for the scientific program. For the public part of the program, such as what we're doing now, and for the honorarium, and for the reception, we've been generously funded by numerous private donors. So I'd like to just spend a few moments extending my thanks to the most significant private donors. In particular, we have gold level sponsorship by the group of companies, Great West Life, London Life, and Canada Life, and they're represented by Linda Kerrigan, Vice President and Chief Actuary for Reinsurance, who I believe is in the hall today. So thank you very much for coming. The silver sponsorship by James Stewart, who is a professor emeritus of mathematics from McMaster University, a famous textbook writer, a famous amateur of music and architecture, and a longtime supporter of the Fields Institute. And he may be here, I don't see him, but it's possible, he registered at least, it's possible that he's here. There's also several numerous bronze level and other contributors to this Fields Medal Symposium, but they're too numerous for me to mention right now, so I'm going to thank them afterwards in private. And I'd like to also say that we have a number of dignitaries, well-known people, and honored guests tonight, and I just want to recognize them and thank them for coming. Monsieur Jean-François Casabonne-Mazenave from the Consulat de France Grenoble, who's the French consul. Thank you for coming. There's Dr. Peter Lewis, who's the Vice President of Research from the University of Toronto. Thank you very much for coming. There's Walter Tholen, Associate Vice President of Research from York University. Thank you very much for coming. And also, there's Professor Andrei Okukov, who's a 2006 field medalist from Columbia University, who will be giving a colloquium lecture on Wednesday afternoon, I believe, if I got that right. I want to also point out that we have extremely hard-working and also actually world-famous symposium organizers. Alessio Figali, who's very active on the organizing committee and also a great mathematician. Robert McCann, who's really been the lead organizer, and I'm extremely grateful for his contribution. Clément Mouha, who's also in the room, and Neil Trudinger, who unfortunately was not able to come. I will finish by bringing your attention to several aspects of the scientific program that will take place over the coming week. Well, we started this morning, so you missed that if you weren't there, but we're continuing until Thursday afternoon. During the day, there are generally scientific lectures by top international experts that take place in the big lecture hall at the Fields Institute. It's almost standing room only, so get there a little bit early. There are additional public events. So Tuesday evening at the Alliance Française, there's a second showing of Comme j'ai détesté les maths, which is an award-winning film by Olivier Payon, which will be followed by a panel discussion with Cédric Villani and Olivier Payon himself, and with Fields Institute Deputy Director Matthias Grasselli, who is busy studying up so he can debate these honored people. There was a prior showing last night at the Alliance Française with a very nice reception. Thursday afternoon at the Fields Institute, there will be a public lecture by John Mighton, who's the founder of JUMP. JUMP stands for Junior Undiscovered Math Prodigies, and for many things, including his playwriting, he's an Order of Canada. He's in the hall today, so thanks very much, John, for coming. His public lecture is in the afternoon. I forget exactly what time, but it's on the web, and its title is Why Teach Math? After that, there will be a second showing of Olivier Payon's second film featuring Villani, entitled En route pour la médaille Fields, and there will be a following program in the early evening for high school students, aimed at high school students and undergraduates. But we ourselves are welcome, as are retired people and anybody who really wants to come. It's great to interact with on a personal level with great mathematicians and with our friends. So please feel free to come. I'm going to continue. I'm going to stop talking very shortly, but I'd like to present our first and a special invited guest, who is the Honorable Reza Moridi. He's the Minister of Training Colleges and Universities for Ontario, as well as the Minister of Research and Innovation. and he's a great friend of the Fields Institute. I'd like him to come up and make a few remarks. So, Minister Moridi.
Well, thank you very much, Walter, for that kind introduction. Good evening, ladies and gentlemen. It's a great pleasure to be here this evening in the company of esteemed guests. First of all, I would like to acknowledge His Excellency Jean-François Casaubon-Massonneau, Consul General of France in Toronto, Dr. Merrick Gertler. I guess he's not with us, but he will join us shortly, I believe. And of course, Walter Craig, the director of the Fields Institute, and Professor Shigemofomi Mori, the president-elect of the International Mathematical Union, and Dr. Mario Pinto, president of the Natural Science and Engineering Research Council of Canada. Congratulations on your first day on the job, sir, as I understand. And of course, Professor Cédric Villani, the 2010 Fields medalist from the University of Lyon from France. Welcome to Toronto, and again, congratulations on winning this prestigious medal 4 years ago. I am pleased to greet so many distinguished mathematicians and students to the 2014 Fields Symposium. Tonight, I have the honor of standing before you in my new dual role as the Minister of Training Colleges, Universities, as well as the Minister of Research and Innovation. My two portfolios have given me further insight into how Ontario's future prosperity is directly linked to our ability to be a global leader in education, training, and in building a culture of innovation and research excellence in our province of Ontario. We know that boosting the innovation and the research capacity of our universities will help drive Ontario's global competitiveness and create knowledge that will bring tangible benefits to Ontario. This province has a long history of supporting and producing world-leading innovators and making new discoveries that have altered the trajectory of history. That's why, despite the challenging economic times, our government continues to invest heavily in post-secondary education and research. And it is paying off. 4 of the top 10 Canadian research universities are here in this province. And we are now producing some of the best and the brightest young scientists and researchers anywhere in the world. In the same way that post-secondary education and the research are directly connected, mathematics forms the core and foundation of all branches of science and knowledge. Advances in physics, mathematics, chemistry, astronomy, medicine, engineering, and even social sciences are all made possible by the application of mathematics. But all too often, mathematics is overlooked. People say they are not good with numbers, and some students shy away from maths courses. It is our job to encourage young learners to approach mathematics with the intellectual curiosity and enthusiasm that is energizing this room tonight, and to support the students so they can follow in the footsteps of our greatest and the great innovators and pursue research that improves our society, our economy, and our lives. It's fitting that the Fields Institute continues the work of John Charles Fields by promoting mathematics as an area of study, especially for young people. In the spirit of international collaborations, I understand that this year's symposium will celebrate Professor Villani's research. with culture programs coordinated with the French consulate in Toronto. So thank you very much, sir, for that. Earlier this month, my colleague, Madame Mayor, Minister of Francophone Affairs of Ontario, signed a Memorandum of Understanding on behalf of Ontario's Learning Ministries with France's Minister of Higher Education and Research. This is part of our government's ongoing support for Ontario's Francophone students. It is critical to include all young people in Ontario as we work to improve their proficiency in maths and sciences and connect them to the leading mathematicians in our country. Since the Fields Institute shares the goals of both my ministries, I am pleased that our government continues to support the Institute. The Fields Medal is only awarded every 4 years, so 2014 is an auspicious year. I would like to take a moment to congratulate the 2014 Fields medalists, Arthur Avila, Martin Herrier, Mariam Mirzakhani, and Ontario's very own Manjul Bhargava on their accomplishments. Yes. But we are here tonight to hear 2010 Fields medalist Cédric Villani's lecture entitled The Many Facets of Entropy. I got to learn about entropy when I was second-year student in physics studying thermodynamics. In 1873, the pioneering theoretical mathematician Josiah Willard Gibbs wrote, quote, "Any method involving the notion of entropy will doubtless seem far-faceted and may repel beginners as obscure and difficult of comprehension," unquote. Well, almost 140 years later, entropy doesn't seem so far-fetched, and we all look forward to Professor Villani's lecture on that very topic. I'm sure Professor Villani will inspire everyone here this evening, especially students, to appreciate the importance of pursuing pure and applied mathematics. So I want to thank you all and wish you a very successful symposium. Thank you again, and merci beaucoup. Thank you. Thank you.
Maybe I'm letting out a secret that I shouldn't, but it's clear that Minister Moridi has his doctorate in physics, as he does. Our next speaker and honored guest is Dr. B. Mario Pinto, who is president of NSERC, and in that sense very important for us. I believe this is his first day on the job, so I'm very happy that he comes and spends time with us, and we can give him an earful. That's our plan. He has been a faculty member and an administrator at Simon Fraser University, a chemist, I think biology and chemistry, if I get it right. And really, I wish to use this occasion to welcome him very warmly to his position and to say that we share his, quote, vision of Canadian researchers playing an even greater role on the world stage, something that I enjoyed, that you can see that directly on the NSERC website. We hope the events tonight and the scientific program of the Fields Medal Symposium live up to his vision and his standards for this. So, Dr. Pinto.
Well, thank you very much for that very warm introduction. It's a pleasure to be here. It is my first day on the job, and it's fitting that I should begin with the foundation, speaking to mathematicians. Right? And I really do believe that. I have to admit that I'm a failed mathematician. I started my BSc at Queen's University in mathematics and computing, but then became frustrated with the lack of interaction with people, and so decided to move more into the other natural sciences. But I continue to use mathematics as a foundation in all my computational modeling of drug receptor interactions, and I've gone on to use that knowledge very usefully in the design of drug candidates and vaccines, and that has served me well. I have just completed 10 years as Vice President of Research at Simon Fraser University, and because of that, I think I have some qualifications to lead the Natural Sciences and Engineering Research Council of Canada. So good evening. And thank you, Walter. That was a very warm introduction. Thank you also for inviting me to join this august group this evening. C'est pour moi un honneur de prendre part ce soir à ce rassemblement unique auquel ont été conviés les membres des milieux canadiens de mathématiciens, des mathématiques et de la statistique. Today, as you've heard, is my first day as president of the Natural Sciences and Engineering Research Council, but I've really been on the job all summer, scouring the country and putting together a strategy for NSERC called Strategy 2020. And you will hear about this very soon as I go across the country. I spent the last week in the Atlantic provinces, starting from Newfoundland, and have received already some very valuable feedback. I'm particularly pleased, as I said, to be spending my first evening on the job with mathematicians and statisticians, people whose work is at the very foundation of science, technology, and engineering. And as the minister has said, it's absolutely essential that we instruct the next generation in all areas of STEM, science, technology, engineering, and mathematics. And that, I think, is a task, is a challenge, and the onus is on all of us to make sure that we succeed and we bring that project to fruition. As one of the leading research institutes in the mathematical sciences, I don't have to tell you that the Fields Institute serves as a model for successful interdisciplinary and international collaboration. At NSERC, we celebrate this kind of collaboration. Collaboration allows students, established researchers, businesses, and others to work hand in hand on the discoveries and innovations that contribute to our quality of life, that have both societal and economic impact. Collaboration ultimately paves the way to solving the problems faced by humanity today, and there are many, as you well know. And the journey to those benefits has undergone a rapid evolution in recent years, rapid evolution in thought. The traditional notions of how research and innovation relate and related no longer apply. Research does not progress down a linear path. It falls back into itself, and I use the Mobius strip as an example to illustrate exactly that. The fluidity of the research pathway where there's no beginning and no end. Rather, a fluid circuit of ideas that leads eventually to advancements. Ce progrès non linéaire a contribué à abolir des frontières qui séparaient les chercheurs universitaires et collégiens et les secteurs industriels et publics. En recherche, tous ont le même objectif et travaillent dans un écosystème poussé, tiré, où les forces motivantes de l'innovation sont partout. On ne sait jamais d'où jaillira l'étincelle qui fera naître de nouvelles idées. And what about the notion that discovery and innovation are distinct entities, distinct and separate? What is that irreducible representation that makes one type of research discovery in nature? Surely, it depends very much on the boundary conditions that one sets. And so I maintain that that distinction between discovery and innovation is an artificial distinction, And we should not be obsessed with that distinction. Discovery, as we all know, is at the heart of all innovation. And we as a community are not doing ourselves any favors by fixating on these artificial boundaries. So I would like to see those boundaries pulled down, and we intend to do exactly that in the coming months at NSERC. We have to realize that we all ultimately want to grow the funding pie and not split it up into smaller individual pieces. And so it behooves all of us to present a coherent front and a cogent strategy where we all profit and we all advance in the areas of STEM. How do we grow that pie? I've already talked about the discovery aspect, the individual scholarly inquiry. That is absolutely indispensable. Without that solid foundation, one cannot develop anywhere. But collaboration is the other piece, right? Through the development of new approaches, different perspectives, at the national level, at the international level, one can develop plans that foster partnerships, interactions, different ways of thinking, different disciplines, spanning, as the minister just alluded to, the natural sciences and the social sciences. This is an important element of interdisciplinary research. And Rabindranath Tagore used to say, to illustrate the point of perspective, the fireflies twinkling among the trees make the stars wonder. And I think it's very useful to have those different perspectives as one collaborates. In 2012, the long-range plan for mathematical and statistical sciences research in Canada was launched and was the result of this very kind of collaboration. The creation of the plan brought together members of the mathematics and statistical community to outline a clear action plan from 2013 to 2018. Fondé sur les gens, la recherche, la découverte, l'innovation et les liens, le plan à long terme pour la recherche en mathématiques et en statistiques au Canada préconise d'accroître l'appui à la recherche en mathématiques et en statistiques. My understanding is that NSERC worked closely with the Long Range Planning Committee and moved quickly to act on elements of its vision. In close consultation with the community, we strengthened our support by creating the collaborative and thematic resources support in mathematics and statistics program. Designed to commit dedicated resources for thematic institutes, the initiative provides resources to organizations like the Fields Institute to establish environments that accelerate research in the mathematical and statistical sciences. I look forward to working with this community and to getting to know you better, to push the long-range plan even further, and to partnering more effectively with you. I am very receptive to your insights, and I'm working closely with you to strengthen NSERC's support for your important work. And I'll give you my commitment to that, Walter. Les brillants esprits qui m'entourent ce soir sont pour moi une véritable source d'inspiration. Votre apport à la collaboration, au mentorat et à la suppression des barrières témoigne parfaitement de la capacité du Canada en découverte et en innovation. I am confident that the namesake of this institute, John Charles Fields, would be proud of your commitment to his legacy of increasing the interaction between researchers, academics, students, and the public. Monsieur Fields serait particulièrement fier ce soir de nous voir rendre hommage à Cédric Villani et de nous entendre parler de ses réalisations pour lesquelles on lui a décerné en 2010 la médaille Fields. Ladies and gentlemen, it's my pleasure to be here once again, and I thank you very much for inviting me to participate in this very important event. Merci beaucoup.
Thank you very much for your very nice and very astute and also interesting remarks on your first day at work, and I look forward to many more further communications with you on the subjects of your talk. Collaboration is a beautiful word. We have a next speaker, which is our honored guest, Professor Shigefume Mori of the University of Kyoto, and now President-elect of the International Mathematicians Union. He will take his offices at the Mathematicians Union on January 1st, and we're already making him work for it. So welcome.
Thank you very much for the nice introduction. Distinguished guests, especially Professor Cédric Villani, ladies and gentlemen, it is a great honor for me to speak here on the occasion of the Fields Medal Symposium on behalf of IMU. Fields Medal has been extremely successful and quite unique in the sense that it is intended to a mathematician under the age of 40 for current achievement and awarded at ICM every 4 years. To be more specific, the restriction is that the person has to be under 40 at January 1st of the year of ICM. Being the oldest and most prestigious prize of IMU, International Mathematical Union, the Fields Medal has formed a strong image of mathematics and made tremendous impact, influence, and contribution to mathematics, not to mention to IMU. So IMU, International Mathematical Union, is extremely grateful to Professor John Charles Fields, who founded the Fields Medal, first awarded in 1936, for his great idea and insight, and also to the University of Toronto for the effort to maintain the tradition. I heard a little bit about how they carry the medal and so on. And as one of the recipients, it is needless to say that I'm personally very grateful to them as well. IMU is now very grateful to the Fields Institute for starting a new tradition of Fields Medal Symposium annually to present the work of Fields medalists, to expose the potential for future directions, to foster the next generation, and to reach out to a broader public. So to foster the next generation is undoubtedly the very important business for IMU as well. So IMU strongly supports this symposium. So this year, Fields Medal Symposium will be about the work of Professor Cédric Villani, who was awarded the Fields Medal in 2010 for his achievement in partial differential equations. Last night, I attended a public event, workshop, and questions with Cédric Villani prior to the academic programs. And I was impressed by his successfully communicating with the general audience. Though I don't understand French, unfortunately, I could feel the atmosphere. I admire this new tradition and believe its overall success again, and look forward to the talk by Professor Cédric Villani tonight. Thank you very much. Sorry for this short speech. I'm still learning.
Well, one principle is no one should ever apologize for giving a shorter speech than expected. But I have to apologize that I gave a shorter speech than I was supposed to, because my paragraph saying that Professor Mori is a widely known mathematician whose field is algebraic geometry, and he's received numerous awards, including a 1990 Fields Medal. So I forgot to say that. I was just a little too discombobbled by the emotion that Mario Pinto gave in me over collaboration. I just did want to make sure that that came into the picture. We are deeply grateful that you're able to come and be with us at the Fields Medal Symposium and this public opening, and also for the events yesterday, today, and tomorrow. Thank you very much, Professor Mori. Okay, we are approaching the main event of the evening, which is a public lecture by Cédric Villani, but it's not up to me to introduce him. But I would like to ask Professor Robert McCann, a colleague of mine at Brown University before he moved to Toronto and before I moved to Canada. And he's also been a lead organizer and a driving force in arranging the beautiful program for this semester. It's a thematic program on variational problems, and it's not far from my own topic, and it's been really very, very inspiring. So thank you for doing that. And I would like to announce in public that Robert is just a recently minted Fellow of the Royal Society of Canada. So congratulations, Robert. So Robert will introduce our evening speaker and his talk with a short introduction entitled Introduction to Cédric Villani. So Robert McCann.
Thank you, Walter, and it's really a pleasure for me to be here tonight and to have the privilege to have the opportunity to tell you a little bit about the life and work of Cédric Villani before we move on to the main event. So Cédric, you know, is a product of this very elite training program for mathematicians, which they have in France. Can you hear me? Is the microphone? Yeah, okay. So at the end, for those of you who don't know, at the end of high school, if you can spend 2 years preparing for a national competition to win a place in one of the grandes écoles, which, if successful, provides you, I think you become essentially a government employee with an income and a pension to study for the next 4 years. And so Cédric was one of the winners in this competition. He graduated from a high school in Paris whose alumni include Victor Hugo and former President Jacques Chirac. And in 1992, he began his studies at the École Normale Supérieure, where he spent the next 4 years. He was, I think he was president of the Student Association there at the time. Everything that he does with great intensity. So I think he was also a very successful partier during some of those years, and somewhat legendary among his fellow students. When he finished in 1996, he spent the next 2 years completing a PhD under the supervision of Pierre-Louis Lyons, also a Fields medalist. So that makes Cédric, I think, the second, and now a third has been added, Fields medalist with a Fields medalist advisor. So the others being Grothendieck, who was advised by Laurent Schwartz, and one of this year's awardees, Miriam Mirzakhani, who was advised by Curtis McClellan. So I don't think there's yet been a third generation Fields medalist, although Cédric has certainly advised some terrific students himself, 2 of whom I've had the privilege of working with together on the organizing committee for this symposium. So let's see what the future will bring. When he finished his PhD, he's actually described, although his formal advisor was Pierre-Louis Lyons, he once described himself to me as an experiment with 4 fathers. So he said that in addition to Lyons, he also considered Michel Ledoux, one of our speakers in the Fields Medal Symposium this afternoon, to be a major scientific influence on him. Eric Carlin, who we hope will join us on Wednesday, an expert in kinetic theory of gases like Cédric himself, and Yann Brenier, who spent the first half of the semester in residence at the Fields Institute in conjunction with our thematic program on variational problems in physics, economics, and geometry. So when he finished his PhD, a special position was arranged for him at the École Normale Supérieure. So in Paris, I don't know how it is now, but it used to be that none of the professors at École Normale were lifetime appointments because it was considered that you were teaching the very best students in France, and so you have to have a little freshness for that. And so there was a certain amount of turnover was ensured, but a special position was arranged for Cédric to spend the next 2 years as a sort of instructor there. But very fortunately for our community, he took a semester off at the invitation of my former collaborator, Wilfred Gangbo, who's also a co-organizer of the program this semester at Fields and will be a speaker in the symposium on Thursday, and spent a semester in Atlanta where he taught a graduate course on optimal transportation, which is my own subject and the subject that Wilfred Gangbo works on. And The result of this course was that, again, Cédric taught the course with great enthusiasm. I understood that it was supposed to meet for 3 hours per week, but he was regularly teaching it for 4 hours per week until the students finally wrote a letter of complaint. And it had to be explained to him that some of the students had another class to go to after his class was supposed to end. But his lecture notes from this course actually became a very successful 2003 publication of the American Mathematical Society called Topics in Optimal Transportation, which many people who had the good fortune to enter the subject after he wrote the book learned the subject from. Those were also the 2 years during which I met Cédric. So I met Cédric at a scientific meeting in Lumini, which we had both traveled from North America to, so we arrived at the airport in Marseille on, I think, perhaps even the same flight. And this is also maybe the first place where entropy enters the story of my introduction to Cédric. So in my PhD thesis, I had studied interacting gas systems, and I had made the following observation that if you, well, it's actually better understood now than at the time, but if you have two distributions of gas, and you imagine getting from the first one to the second one following the physical path of least action, so that they're non-interacting gases, so you just move as lazily as you can from the first distribution to the second one, and you measure the entropy of the gas as you're moving from the first position to the second one, it turns out to be, the physical entropy would be a concave function of time as you move from the first position to the second one, so it would be larger in the middle than it was at either end, typically. And so actually both Cédric and I at that time had been interested in trying to extend this observation to gases which lived in curved geometries like the surface of the Earth. And the Cédric in collaboration with Felix Otto, who gave a beautiful lecture this morning, and myself in collaboration with Dario Cordero and Michaela Schmuckenschläger. So if you imagine that your gas particles live on the surface of the Earth and they want to move from one pole to the other, say, they get very spread out in the middle because of the curvature of the Earth. And so entropy, which is kind of a measure of randomness, is actually much larger in the middle than it would have been in flat space. And this is an observation from Cédric and Felix Otto's work, and also my work with Dario Cordero and Michael Schmuckenschläger. And it was later realized by Karl Theodor Sturm, who's also in the audience tonight, and will give a talk Wednesday morning, that this observation that this curvature is bigger, I mean the entropy is larger if the curvature is larger, is actually an if and only if observation. So in other words, if the curvature is not larger, you can find two distributions of larger than zero, say. You can find two distributions of gas such that when you move as lazily as you can from the first distribution to the second distribution, the entropy will not be larger than it was in Euclidean space. And together with John Lott, Cédric Villani on the one hand, and independently Karl Theodor Sturm on the other, built this observation into a beautiful theory of metric measure spaces with curvature bounded from, Ricci curvature bounded from below. So there are different technical notions of curvature, and the relevant one in this context is the so-called Ricci curvature, which is a kind of average curvature that, for example, it comes up in the theory of gravity. Kip Thorne has a beautiful thought experiment that says if you were a captain of a spaceship orbiting a black hole, and you wanted to explore the geometry around this black hole, and you lowered your spaceship towards the black hole, you would eventually start to feel, if the mass of the black hole was correct, your head stretched away from your feet and your sides pressed in the middle, and front to back and side to side. And this would be a manifestation of this curvature of space-time, which was Einstein's explanation for the nature of the force of gravity. It's also the effect that makes the Earth bulge towards and away from the moon. So it's the effect that causes the tides. So this is an example of Ricci curvature. And an open question, which was solved in the work of Cédric and Felix Otto, and also independently Karl Theodor Sturm, was can one make sense of this notion of Ricci curvature in a space which is not too smooth? So not smooth like the round sphere, but maybe has corners like the cube or some perturbed roughness, where all the information you have at your disposal in order to try to understand curvature is a notion of distance in the space, maybe a notion of shortest curves joining pairs of points, shortest curves joining particles of gases, and a measure or a volume that tells you the amount of mass in any ball or the amount of volume in any ball in the space. And they were able to make this into a very successful theory and extend many beautiful classical theorems from Riemannian geometry to this new rougher setting, which has developed very rapidly in recent years, and we hope to see exciting applications, perhaps even in classical differential geometry, come out of it. However, this was not the work that Cédric was awarded the Fields Medal for. So in the year 2000, he took up a professorship at the École Normale Supérieure de Lyon, which, being outside of Paris, they decided that as a recruitment incentive, it would be useful to have permanent professors in Lyon. And so he was a permanent professor for 9 years in Lyon. And towards the end of those 9 years, he won a succession of very distinguished prizes, a prize of the National Academy of France, the European Mathematical Society Prize in 2007, or maybe 2008, the Poincaré Prize of the International Association of Mathematical Physicists, and also the Fermat Prize in 2009, and culminating in his 2010 Fields Medal. So in the Fields Medal citation, they cite contributions to 2 different problems coming out of the kinetic theory of gases. So this is really the area in which Cédric is probably one of the world's leading expert. And it's really an area where you want to understand the effect of nonlinearity in the time evolution of physical systems. So he worked on 2 problems, one in collaboration with Laurent Deviette, and the other in collaboration with his former student Clément Mouot. And so let me take a few minutes to describe a little bit these 2 problems. So the first problem concerns what's called the Boltzmann equation. And so you should imagine that it models a system like the gas in this room, and which involves trillions and trillions of particles moving around and colliding into each other every minute, every second. And what you want to understand is the dynamics of this behavior. For example, if one corner of the room is hot and the other corner of the room is cold, how long do you have to wait? And the gas can move around, the molecules bump into each other, some move faster, some move slower. How long do you have to wait until the room comes into thermal equilibrium, until we see the same temperature everywhere? And this sort of problem reminded me very vividly of an experiment which I saw carried out, I think in grade 6, where my elementary school teacher heated an empty olive oil can to quite a high temperature. There may have been a little bit of water in it in class, and then he screwed the cap on. It was a metal can, and then he set it aside, and we continued with the lesson. And over the course of the next 20 or 30 minutes or so, can you imagine what happened? So the heat had caused the air inside the olive oil jar to evacuate, and so it was much lower density inside, and so as it cooled down, the can actually imploded and crushed itself quite dramatically. So in this sense, this is the kind of time scale of relaxation that one wants to understand. And Cédric and Laurent Deviette were able to understand this in the context of something called the Boltzmann equation, which was formulated 150 years ago. And it's an equation which, there are these trillions and trillions of molecules in the room, and it would be impossible for us to try to keep track of the location and velocity of every one of them. So we adopt a more probabilistic point of view, and what we try to keep track of is the probability that at some point in the room you will find some number of particles with a certain velocity. So this probability depends on both the position and the velocity. And Boltzmann's equation is kind of it's an ansatz, or it's a hypothesis for how these probabilities should evolve. So if we know all these probabilities at time 0, how will they look at some later time? And the ansatz, the evolution is based on really 2 ideas. One of them is that if you have a particle here with velocity v, it's going to move in the direction of its velocity following a straight line with constant speed. So that's one effect, the linear transport effect in the equation. And the other effect in the equation is the nonlinear effect. It's a quadratic effect, and the idea is that all of the molecules at a given point in space, they all have different velocities, and you make a hypothesis that the probability that 2 of them will, that if 2 of them collide, the hypothesis is that, first of all, the velocities of the 2 colliding will be randomly and independently drawn from the distribution of velocities at that point in space. And secondly, that they will scatter off each other in some way with a certain probability. They will deflect to some certain angle in a way that's consistent with the symmetries of the problem and conserves angular momentum and total energy. And the question was, if you hypothesize these 2 effects, will the equation predict the evolution that we expect it to? Will we see that the hot parts of the room grow cooler and the cool parts grow hotter until the whole room is in thermal equilibrium? And as Boltzmann had predicted and expected that one would see, but no one had been able to prove. And this evolution turned out to be very intimately connected with the physical notion of entropy. And Boltzmann himself made this observation that unless the distribution of gas at each point in space forms a bell curve, so is normally distributed around some average velocity, the collisions have a kind of central limit theorem effect of randomizing things, and that tends to drive things towards bell curves. And unless the velocities of the gas at each point in space are distributed like a bell curve, the system of the entropy will increase. So his observations were, first of all, the entropy never decreases, and secondly, it will strictly increase unless the distribution of velocities has a normal distribution at each point in space. However, this normal distribution has a variance and a mean, and there's nothing that says the variance and the mean at one point in space, which is to say the temperature of the gas, has to be the same as the variance and mean at some other point in space. And so somehow the fundamental insight that de Viette and Villani brought to this problem was that they identified a mechanism which says, even if you have a normal distribution at every point in space-time, if the variances and the means are different at different points in space-time, the distributions are not going to stay normal very long. So in other words, as the particles move, they were able to quantify the sense in which this normal distribution gets destroyed, and then the entropy starts to increase again according to Boltzmann's principle. So the principle of increase of entropy had actually been quantified, I think, perhaps a little bit earlier by Eric Carlin and Sal Carvalho to say, if you have the same distribution of velocities at every point in space-time, but it's non-normal, then you can see the rate at which it's going to normalize. And what Villani and de Viette were able to do was say, if you don't have the same distribution at every point in space-time, not only will it start to normalize at every point in space-time, the normal distributions will start to have the same variance and mean. And they were able to predict quantitatively how long do you have to wait for this to happen. So in other words, how long do you have to wait for my gas can or olive oil can to crush itself? And what they discovered was that although the linearization predicts maybe an exponential rate of convergence, they were really interested in treating the nonlinear terms, and they showed that we don't know, I guess we don't know, or the convergence rate will not always be exponential, but what we can always say is that it's faster than any algebraic rate. So it converges faster in time than a polynomial. And the second problem which Cédric solved, which is quoted in his Fields Medal citation, is actually closely related to this, but much more technically sophisticated. So it's also a problem of the long time dynamics of an evolving gas, but it's a gas in which the particles have either charges or masses. And so they interact with each other not through collisions, but either through electrostatic repulsion or gravitational attraction. And for the questions he addressed, it turns out not to matter whether we're in the repulsive electrostatic case or the gravitationally attractive case, but the applications are very different. So one is the physics of plasmas, and the second one is the evolution of galaxies, basically. It's again a kinetic theory model, which means we're interested in the evolution of a probability distribution, the probability of finding a certain number of particles at a certain point in space with a certain velocity. But the interaction this time through the electrostatic or the gravitational interaction is time reversible. And since it's a time reversible interaction, one wouldn't necessarily expect to see quantity like entropy increase. And so Landau had stunned the mathematical and physical world some 75 years ago by predicting that even though this equation was reversible based on a linearization, he predicted that if you started from an equilibrium state which was linearly stable and you perturbed it a little bit, that the electric field would damp out. So not only would you stay close to the perturbed state, but the electric field would actually tend to zero. And so in some sense, you might expect to see some kind of asymptotic stability. And so there was sort of a philosophical paradox. First of all, there was a philosophical paradox. The equation was time reversible, but the prediction of Landau was not. And secondly, there was an experimental paradox because in a lot of situations, you did see this kind of stability, such as galactic dynamics, but in others, this stability seemed to be violated. So there were experiments which you might have expected to be stable based on this prediction, but weren't. And so Cédric and Clément's contribution to this area was to resolve this question by fully treating the nonlinear aspect of the evolution once again. And what they discovered several things, but one of them was that the sense in which you measure stability really matters. So if you have a very smooth perturbation away from one of these equilibrium states, or say analytic, then the electric field does indeed decay to zero as time goes to infinity. But it was known, I guess, before their work that if you had small but rough perturbations, you could easily kick the system out of equilibrium, and that probably explains the physical paradox of the experimentally observed instabilities. And they also observed that the mechanism for this convergence back to equilibrium was really an averaging mechanism that involved transfer of regularity. So you have maybe spatial inhomogeneities, the velocity profile at different points in the plasma or gravitating system are different from each other. As those start to even out with each other, they're compensated by the appearance of oscillations in the velocity variables. So you start to see the same picture across different areas of space, but you start to see high oscillation in the velocity space. But this, because it's an electrostatic model, so we're assuming that everything is moving slowly enough that we can neglect the magnetic interactions and we only keep track of the electric interactions, you never see this at the level of the electric field, these velocity oscillations. Okay. So finally, I would say that more than any other fields medalist that I'm aware of, Cédric has embraced his role as a kind of public ambassador for mathematics. So he's, in fact, become a media sensation in France. I think he's been called the Lady Gaga of mathematics. He appears in a number of films on the subject, including the world premiere of a 50-minute documentary devoted to Cédric himself that we saw yesterday at the Alliance Française and which will be repeated on Thursday at the Fields Institute. He also plays a role in the award-winning documentary by the same filmmaker, which will be shown tomorrow night at the Alliance Française, to be followed by a discussion panel and co-sponsored by the French consulate. He's written a very successful book called Theorem Vivant in France. The English version is called Birth of a Theorem and is due out next March, but he has a preview which he was kind enough to allow me to share with you. And and he's undoubtedly the best spokesperson for the subject, and so let me invite him to the stage to give his lecture on the many facets of entropy. Congratulations.
Thank you very much. Okay. Okay, everybody hear me well? Thanks very much. It's a great honor to be here in this symposium. It's a great honor to be honored by this symposium. And it's also great to have been introduced in such a warm manner by various people and by Robert recalling all these years that we have known each other and worked on subjects of common interest. In this lecture, this will be public lecture, so supposed to be intended for people with no particular mathematical background. That was the mission, right? So it will be a small subset of what Robert was kind enough to recall, but explain with more, let's say, how to say, yes, more wrapping, you know. And it's not exactly the same title, but that's almost the same, you know, many faces or many facets. Actually, the many facets of entropy was suggested by Robert, and when I saw this, I recall this was the title of a lecture by long ago by a specialist of Boltzmann equation, Harold Grad, from Courant Institute, who did a lot of work. Yes, maybe Walter, you knew him, who did enormous work to transform the Boltzmann equation into a mathematical subject in the footsteps of Kahneman. So this is also a homage to Harold Grad, this title. Harold passed away long before his term was due, and he was extraordinarily inventive, as can be seen in his articles. So today, we'll insist on one of these aspects of entropy and enumerate a few other use, and before that there will be some preparation. So one of the focus will be about a certain topic in which entropy plays a key role, or two topics. So there will be the kinetic theory, there will be the optimal transport, but let's start with some reminders about the nature of mathematics. So this image I like to present at the beginning of some public lectures about mathematics. Maybe some people will recognize this is the Lady of Shalott. It's the hero in some, she's in some poetry by Alfred Lord Tennyson, and I first actually heard about her in a song by Lorena McKennitt that many of the Canadian people here certainly know. And this poem, The Lady of Shalott. So this is from the times of King Arthur. And she has been struck by a curse so that she is forbidden to look at the world directly, only looking at the world through the reflection of the mirror that you see here on the left corner. And in the legend, one day passes Lancelot outside of the window, and he's so handsome that she looks at him directly, and then she's struck by the curse, and she dies, and her body drifts on the water, and so on and so forth. It's very tragic. And, you know, there has been wide speculation about whether there's a hidden meaning for the poetry. And because the author left no explanation, I like to think that this is an allegory of the mathematician. Here, that's the mathematician, and she cannot explore the world by directly doing experiments, only by studying the reflection of the abstract formulas and equations. And that's really us. This is distinction at the beginning with the physicists. Physicists can do experiments to test their assumptions, but mathematicians are only allowed to make the tests on the reflection, which is the world of mathematical logic. And this is where everything will be decided. And, you know, because the mathematicians only work in the abstract, there is a drawback that we have to work on this without being able to test with experiments. But there is an advantage, which is that the conclusion in the world of mathematics can have many different applications to various objects and situations. And in the hero of today, entropy, that's precisely the thing. Once this is a mathematical concept, it can be applied to many different physical problems. Here, I put a few formulas and a few objects which are typical and emblematic of this capacity of mathematical objects to have repercussions in many different systems. Let's add that mathematics, and it's important to insist in public lectures, is a subject which still evolves very quickly, in fact, quicker than ever, with hundreds of thousands of new theorems proven every year, and hundreds of thousands of living mathematicians, certainly more mathematicians alive than the total number of all the mathematicians from the past who are deceased. And this is a field in which there are many problems which are solved constantly, in which the number of problems to solve is also continuously increasing. Because the more you solve problems, the more there are new problems to solve. And this is a topic in which changes are faster nowadays than they were in the past. It's important to insist on this also because there is this conception for many people outside our field that mathematics is a subject that was completed, say, in the 19th century, and that we are just working on applications and so on. So nothing can be further from the truth. Now, all mathematicians have their favorite problems, and if you ask them which is the most important problem to solve, they will come up with different answers. For some people, it will be problems about fluid mechanics. For some, it will be problems about whatever, number theory, etc. But if you ask them which is the most famous open problem, then probably they will answer Riemann hypothesis. And this certainly is emblematic of the open problems in mathematics. Riemann hypothesis was stated by Riemann more than 150 years ago, and is very simple to state for people who have just a little bit of mathematical background. But I will not go into detail, but just say that. Wait, do I have a pointer here? Middle button, super. So it's about a certain function defined by Riemann and which is related to the prime numbers, denoted by P here. And this function is defined on the plane. So for each point in a plane, you have a certain number, complex number, and you ask in the Riemann problem when this number vanishes. Okay, we know of certain particular places where it vanishes with integer coordinates. We ask whether there are other of these points. Turns out there are infinitely many others. And Riemann thought that they were all on the same line, these points where the function would vanish. Okay, and when you hear the problem, and if you're not a mathematician, you say, okay, let's just compute where it vanishes and check if Riemann was right. And ever since there was development of computers, this has been checked. Ever from the 50s, Alan Turing made programs to compute the zeros of the Riemann function and so on. And it was found that always, all the time we computed the zeros, the values where it vanishes, they are indeed on the same line. And it has been found so for, I think, thousands of billions of these zeros. Always works. But, and that's one big thing about mathematics, if there is one difference with the other sciences too, that's the only field in which 1 billion of experiments which give the right result are not considered as a proof. You know, in any field, not only in sciences, in any field that mankind has invented, if you have, say, 1 million of clues that go in the same direction, then you consider it's done, and you have a certainty. Usually you don't wait until you have 1 million. But in mathematics, even with 1,000 billions of clues that it is right, it is not sufficient. And that's because the mathematician wants the absolute proof based only on the logic that will give no room for the smallest possibility that it is not always true. And this is a real something really different about mathematics from the rest. Why is this important? Why would one care about the Riemann hypothesis? 10 years ago, journalists from The Guardian fantasized that if it was solved, it could bring disaster for internet. It's not very clear, even for mathematicians in the audience, why that would be true. In fact, for mathematicians in the audience, it is clear that this is false. The reasoning was the following. Because the Riemann hypothesis is related with prime numbers, and in fact with the distribution of prime numbers among integers, and because prime numbers have been for a long time a popular way to do very efficient codes that you cannot break, the idea was that if we solve the Riemann hypothesis, then the pirates can crack the codes very efficiently by finding the prime numbers, which are making up a big number. Why is that false is very clear, because if you understand just a tiny bit of the Riemann hypothesis, you know that if it is true, it means that the prime numbers are distributed kind of randomly in a regular way that you can predict the statistics, but it is kind of random. Now, if you want to find prime numbers, what in hell does it help to know that it is randomly distributed? You know, not much. Also, what is more, now it has been abandoned. It's not prime numbers any longer, which are used for the most efficient method of encryption. So even if that would be the case, it would not affect security on the internet. But anyway, mathematicians don't need this kind of sensational claim to love the Riemann hypothesis. They love it and they know it's important because it's related with prime numbers, so it's fundamental, it's simple to state, it has eluded efforts of mathematicians for a very long time, and also it's related to many areas of mathematics and physics. For instance, there is deep connection, still not understood, between the statistics of the places where this Riemann function vanishes and the levels of energy of an abstract atom, problem called eigenvalues of random matrices, large matrices, and anyway, there is model of atom that is as abstract as can be, and for some reason, the levels of energy of this abstract atom are very closely related to the zeros of this Riemann function. Why would there be a relation between the prime numbers and quantum theory? This is a mystery. And the idea is that when this mystery is solved, this will establish the connection and we understand much more on both sides. That's the kind of thing that mathematicians like. In this talk also, we'll see a problem in which we understand the connection and then this opens up paths because you understand better what is on each side of the bridge. Now, it will be useful also to know another contribution of Riemann. Riemann developed non-Euclidean geometry. Euclidean geometry is geometry of a plane, say, in which you have triangles and circles and what we do in high school. In the world of non-Euclidean geometry, units of length may change from place to place. There's no notion of line. It makes no sense to have a line on a curved surface, for instance. But there's still a notion of shortest path, which is called geodesic. Like the trajectory that the plane should have to go from Paris to Toronto and spend the least amount of fuel. If you look on the map or internet, the trajectory of the plane is something like this. It's a curved path and it has been chosen to minimize, roughly speaking, the amount of energy which is spent, the amount of petrol which is burnt. Now imagine you look at all these various curves which minimize the length, all these geodesics. How do we understand their geometry and how do we approach them? One possibility is to compare them with the lines drawn on a sheet of paper. If two geodesics have a tendency to get closer to each other than do lines on a sheet of paper, then we'll talk of positive curvature. And the key feature allowing us to detect positive curvature is that triangles will tend to look fat. If, on the contrary, the geodesics tend to separate from each other very quickly, we'll speak of negative curvature, and triangles will look skinny. Here is an example. In this picture by artist Escher is represented the so-called hyperbolic geometry. Units of length change from place to place, and each of the fish here has the same length as the other fish. In fact, the space is infinite. You see the number of fish is infinite because when you go closer and closer to the boundary of the disk, the apparent length of the fish starts to be extremely small. And the curves that you see here in white are some of these geodesic curves in this space. If you look at a triangle made of geodesic curves in this hyperbolic space, it will look skinny. For instance, the sum of the angles is less than 180 degrees. This is a sure sign of negative curvature. On the other hand, if we look at geodesics on a sphere, they will form triangles which are fat. The sum of the angles, for instance, being more than 180 degrees, and this is positive curvature. Notice the sum of the angles here is 3 times 90 degrees, so 270 degrees. Notice also, if I look at these two geodesics, starting from this point, so they first separate from each other, but then they will meet again at the opposite point from the starting point. So they will become very close again. This is very different from the behavior of two lines in the plane, which, if they intersect once, will never intersect each other again. So geodesics will tend to get closer. This is positive curvature. Okay, now curvature gives rise to beautiful shapes, as can be seen through these images from the Hyperbolic Coral Reef Museum in Dublin. Look at this. This looks like coral a little bit, but it has been constructed using a simple mathematical rule. This is hyperbolic knitting, such that the curvature is negative and such that, in fact, the geometry is the same as the geometry of the hyperbolic space that we saw just before. And if you compute the curvature, there are formulas for this, it will be constant negative. This is also the same in this pseudosphere, which was in display a few years ago at the Cartier Foundation for Contemporary Art in Paris. And it's again the same as on this kind of spinning top, that espèce de toupie, which is up there and comes from a problem of mathematical physics. This picture got an award in a competition of digital images. And if you take one of these small bits here, which are making up the spinning top, each of them will also have exactly the geometry of the hyperbolic space. In fact, it looks like a horse saddle, each of these pieces, and that's typical negative curvature. So there are two things that we can see here which are important in the nature of mathematics. One is the fact that it can make beautiful artwork, and the other is the fact that with one concept you can encompass several situations. You see here, pseudosphere, hyperbolic coral reef, and the spinning top here coming from a problem of mathematical physics, three different shapes, the same geometry, only the hyperbolic geometry of negative curvature, illustrating what Poincaré said once about the nature of mathematics is the art of giving the same name to different concepts. And in the case of entropy also, that will be true. Now, let's conclude about Riemann by saying that he was an absolutely great scientist and that his work was influential for mathematicians first, like was the case with Ricci Corbastro, Italian differential geometer of the beginning of the 20th century. But also the notion of curvature was taken back by physicists. This was mentioned by Robert McCann in the introductory speech, and it was a surprise that this curvature developed by Riemann and by Ricci became the central, the cornerstone of the theory of general relativity of Albert Einstein. This going back and forth between mathematics and physics is very common. Will be also important here in entropy, and this is one of the most famous examples in which a discovery first developed by mathematicians for the sake of curiosity then becomes a key physical concept, in turn bringing back new problems of mathematics from the physics. General relativity has only one application so far, but it's non-negligible, and this is GPS. Because if you don't use the relativistic correction in the computation of the position from the signals of the satellites, then you don't get a precise position from your GPS. And also, it reminds us that in all technology, there is often a bunch of mathematics and theoretical physics. Riemann, of course, has had no idea that curvature would be used one day to make this kind of device. And conversely, people who use the GPS usually have no idea that it has been made using the theories of Riemann, Einstein, and others. And it's good to recall in both directions. The work of the theoreticians once may be used in technology, and you never know where and when. And the technology often uses the work of theoreticians from before. And let us add that Riemann was also very much interested in mechanics of fluids, understanding in particular the singularities, like the one you can see forming in the air in the wake of a supersonic plane or of a Kalashnikov firing. You see here the beautiful mathematical shapes in these perturbations in the air, like pyramid, like a sphere and so on. And Riemann was the first to try and understand them. And in fact, Riemann worked on nearly anything, which makes it extremely impressive when you contrast the list of topics named after him, which mathematicians are still working on, and his lifespan, so that Riemann passed away before my age now. This makes Riemann a very inspiring figure, and that's also something important to recall. The great mathematicians can be very inspiring people. Actually, once I met a very famous rock singer who told me that she goes from time to time on the grave of Riemann to get some inspiration. Artists inspire everybody, but also mathematicians can inspire artists and other people. And I also like to go and visit graves, as can be seen on this example. This is a central cemetery in Vienna. So here, this is another great guy, Ludwig Boltzmann, the father of the mathematical notion of entropy. Entropy existed before Boltzmann, was developed by Clausius and other people as a way to understand thermodynamics, which is the science of exchanges of energy and variations of temperature and so on. But with Boltzmann, it was given quite a different twist. It was in connection with the atomistic theory. Let us recall that before 1910 or so, atoms were considered just a theory. It is only between 1910 and 1915 that it became accepted widely by the scientific community after the book of Jean Perrin in particular. But it was developed strongly by physicists like Maxwell and Boltzmann ever since the 1860s. In this world that Maxwell and Boltzmann had in mind, which is our world, matter is made of many, many tiny atoms that you cannot observe, and if it is in a gas, they are in constant agitation. In those days, they did not have the idea of molecules made of various atoms, and it was perfectly sensible to think of atoms as round spheres, something which is still good to use in many problems of statistical physics to understand the effect of the many-body situation. So let's imagine a gas as a bunch of molecules which are spherical and bump into each other constantly, with changes of velocity, like a huge billiard game, just made of billions of particles. And it takes a lot of effort of imagination. It was almost like poetry, you know. If you think about the air in this room and we try to associate it with a mathematical number, certainly the number would be 0 because the air is still and we don't see any motion. So it's a very real shock when you realize it's made, in fact, of so many of these particles going in all directions in crazy motion, in such a way that if you try to follow the trajectory of any of these particles, you will lose it immediately. It's going in all kinds of ways and directions. This was the wild world imagined by Maxwell and Boltzmann, and they were developing the consequences of this vision. If you are interested in a gas, you cannot hope to consider the evolutions of these particles. But you can look at the statistics of this gas. And Maxwell here and Boltzmann developed the formalism, or continued this push the formalism in which you model a gas through the distribution of velocities. How many fast particles, how many slow particles. And this we can think of for non-mathematicians in the same way as a familiar object as soon as you study geography or demography. which is the distribution of ages in a population. How many old people, how many young people, and you have this pyramid about the ages. And here it's the same, except that it's not the age we're interested in, it's the velocities of the particles. What do you do then once you have this statistical distribution? Well, the contribution of Maxwell and Boltzmann took place in a long stream of thought about mastering chance, starting with Bernoulli in 1700 or so to make up the rule of statistics. Take a coin and toss it in the air, you don't know if it will be head or tail, pile ou face. But if you toss the coin 1,000 times, then we have in mind that it will be, roughly speaking, 500 of each. And if we throw it in the air 1,000,000 times, you have in mind it will be 50%, 50%, even much closer. That's the miracle of statistics. Unable to predict the outcome of one experiment, you may be able to predict the outcome of an enormous number of experiments, provided you turn to the right question, which is the statistics. Around 1730, Abraham de Moivre, who was a Huguenot, emigrated from France to England to seek for religious asylum, observed this Gaussian law for the first time. We call it Gaussian law, but this really should be called the Moivrian law. Something like exponential minus x squared. Anyway, it's this bell curve describing the fluctuations of the statistics. When you toss your coin in the air many, many times, and you ask how much will be the error from 50%, 50%. Most of the time, the error will be small, and this considered to the region in the center here, small deviation with a big probability. And sometimes the deviation will be large, maybe all of the trials give head, but this probability of this large deviation is very small, and that's the meaning of this very small tail here. And he discovered this is the case also for other laws than the head and tail game with the coin. Okay, let's keep Buffon. This was to show that probabilities also, statistics also applied sometimes to experiments with geometrical content, like the needle experiment, in which you throw a needle here on a parquet and ask which is the proportion of times the needle crosses one of the lines. And let's move to Laplace, who was the first to give a decent mathematical proof of the law of errors, showing that for any kind of random system that you observe statistically by performing a large number of experiments which are independent, you end up with these Gaussian fluctuations, these bell shape for the distribution of fluctuations. This was a very tricky mathematical theorem, and still today it is an elaborate mathematical theorem that requires some skill to prove. The law of errors, showing the universality of this bell-shaped curve in describing the fluctuations for statistics. About 30 years later or so, Adolphe Quetelet in Belgium observed that this law of random causes, this law of errors, does not only appear in problems like tossing a coin, but also appears in problems with human sciences. For instance, distribution of crimes from city to city. And it is only after that that it was adapted to physics. This is one rare example in which a concept from mathematics is adapted to social sciences before it is adapted to physics. Let's make a last interesting contribution in this with Francis Galton at the end of the 19th century, discovering that the Gaussian distribution arises in many statistics, for instance, with living beings, for instance, distribution of the size of animals in a species, and he's fascinated by this. Here is a text by Galton. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of frequency of error, the law would have been personified by the Greeks and deified if they had known of it. It reigns with serenity and in complete self-effacement amidst the wildest confusion. The huger the mob and the greater the apparent anarchy, the more perfect is its sway. It is the supreme law of unreason. This is nicely said, emphasizing on the fact that this law is always unescapable. It will be here, and you will encounter it in many more situations than you believe. So far for these statistics and the bell-shaped curve. Back to Boltzmann. What does Boltzmann do in this respect? First, Boltzmann introduces this famous concept of entropy. You see here the formula above the head of Boltzmann. S is K log W. That's the defining formula for entropy. It has been engraved on his grave in Vienna. S is the entropy, K is a constant, whatever. The important thing here is W. W is the number of possibilities of possible states in which your system can be. When you are making the observation of your system, because you are making observation, this gives a limitation on the possible states that the system can be. But what you are observing is only part of the truth, only part of the system. For instance, if you are observing a gas, you never have access to all the positions of the particles in the gas. So even though you are making many experiments, maybe you're measuring the pressure and the temperature and the velocities and many things like this, you'll never be able to measure where exactly are the various particles. And this gives a lot of possible states for the system, and this you call W, and the logarithm of W will be the entropy. Logarithm, think of it as the number of digits that you need to write up the number. This formula so measures the complexity of a situation. If a situation is very hard to appreciate, very disordered maybe, then the entropy will be very large. If the situation is easy to reconstruct from experiments, then the entropy will be very low. I always mention, so some people in the audience already heard it, the story behind this picture was 2006. There was this conference in Vienna to commemorate the 100th anniversary of the death of Boltzmann. And as one specialist of the entropy, I was one of the guests. And I knew that Boltzmann was buried there, so paid a visit to this central cemetery to find him. In Central Cemetery, it's totally huge, and you can spend your whole day walking through the cemetery without finding what you're looking for. As I had no idea where was Boltzmann, I was completely lost, and so needed some help. There was nobody for help, but then I saw some people who were resting on a bench, and I asked them, do you know where I can find a map of the cemetery? And they said, there is no map, nothing, no desk. Who are you looking for? And I answered, Boltzmann, thinking maybe they have heard of him. And the father of the family looked at me with shiny eyes and said exactly, haha, S is K log W. You know, it was like secret code, buzzword between the people in the know, and he took me directly to the tomb where this picture could be taken. See the power of the formula. The entropy, indeed, is a very powerful concept. Let me quote Claude Shannon, father of information theory, who discovered long after Boltzmann that entropy was also key in quantifying the information of a language. and in understanding how much information you can send through a channel, maybe from computer to computer, from cell phone to cell phone. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. It may seem strange that for the same quantity, Shannon is hesitating between information and uncertainty because these look like opposite of each other. It's all a question of point of view. In the idea of Shannon, it is the uncertainty which makes the value of an information. Meaning, if in advance you know what the content of a certain message will be, there is no uncertainty in advance, then there is no information when you decode it. If you know in advance that a guy will say always the same speech that you already heard 1,000 times, then no uncertainty, no information. And if on the other hand, there is something unexpected which is coming in the speech, and this gives information. So in the theory of Shannon, actually, information comes from the rare signals, the rare words. The more a word is rare, and the higher is the value of the information which is associated with this word. And then he discusses this with John von Neumann, who had a better idea. You should call it entropy for two reasons. In first place, your uncertainty has been used statistical mechanics under that name, so it already has a name. In second place, and more importantly, no one knows what entropy really is. So in a debate, you will always have the advantage. We know that von Neumann was known for being a nasty person, so it's not surprising, this comment. It's also true that because of the choice of the word, many people are fascinated by entropy, not just the concept, but also the word. Let me give examples to illustrate more what entropy really is, so that we see that it's possible to explain really what it is. So this is what I told you already in a statistical description which is less precise than the full description. This leaves a huge number of possible states, and the logarithm of this number is called the entropy. So entropy is associated with disorder, but also with information. Let's consider the situation in which you put all the particles in a part of a box. You see, this is a big box. You separate it in two halves. In one half, you put particles. In the other half, zero particle. Once you have this, you have an a priori information on the gas, on the particles, that all particles are on the right. So this gives less uncertainty. And if I pick up one particle from this, I already know that it is on the right compartment. So this gives room for less information. On the other hand, if the gas is free to move everywhere, then there is more uncertainty. The gas is not necessarily on the right. Maybe he is on the left. One extra bit of information, right or left. It's one extra bit of information for each particle. So this is a lot of information, in fact, as a whole. This situation, intuitively, we think of it as more disordered than this one. Of course, here the gas is all tidily put in the right. Well, here it is anywhere, so there is more disorder. You see here, disorder comes with information. And by the way, one last anecdote, funny anecdotes about entropy. Once I was invited on some interview on some television, and in the end, after, when it's, taking off the makeup and whatever, the journalist who had made the interview asked me, now here you see this wall, this white wall, where all the people who are interviewed put some inscriptions. Feel free to write whatever you want as a testimony of your passing here. And I wrote the formula for the entropy, why not? And I wrote désordre et information, disorder and information. And he thought about it, he looked at it and said, that is great. It could be the motto of our channel. La devise de notre chaîne, désordre et information. And he was proud by saying that this is better than order and disinformation. So what happens in this situation, to come back to the physics, well, we know it. The vacuum will aspire, will suck in the gas. And we're used to think of this, that the void is something which has a power of attraction. But in the eyes of Boltzmann, it's not that there is this power of attraction of the vacuum. It's just statistics. It is because spontaneously, the collisions between particles will have a tendency to make the disorder increase. So we'll go to a situation of higher entropy. And this will be responsible for the gas occupying all the space, because this is more disordered if you occupy all the space, if you spread everywhere, rather than being in a neat way in some part of the box. So Boltzmann was giving us a new way to think about it, replacing an idea of something deterministic by the idea of something which is based on randomness in the end, chaotic collisions. So it's a very important change of point of view on why some things occur. You may say, this is weird. If this behavior is based on entropy, disorder, statistics, then it should occur sometimes yes, sometimes no, because it's statistics. But Boltzmann will tell you, no, this occurs always because of the numbers involved. Let's make a small calculation about the freedom of the gas. Imagine that the gas is in the box, we have 10 to the 17 particles, which is quite reasonable. And then let us ask, how much more space does this give the gas to be occupying the whole box rather than the half box? So we look at the number of possibilities for the gas to occupy the full box compared with the number of possibilities for the gas to be only in the half box. Now, because there are so many particles, if you look at this ratio, it will turn out to be much larger than the volume of the galaxy divided by the volume of one proton. Actually, it's even more frightening than this. You should put a large power to that. So imagine a little bit, take the galaxy from here, one proton, then expand the proton in the side of the galaxy, take one proton inside and do this process 200,000 billion times or so, and you arrive at this. When you are looking at such numbers, there is no way that behavior can be random. The probability will be so huge that things will always occur. And that's why these conclusions of Boltzmann based on statistics, because the atoms are so tiny, they hold true always. And we'll never see a gas going spontaneously to a state which is more ordered. That is a classical gas. That is good, but remains one problem. The entropy, how do we compute it? Because this is not very explicit, this is an abstract formula. This is where Boltzmann gives a huge contribution by giving another phase to entropy, a phase that you can compute. A formula depending only on the distribution of positions and velocities. This is a deep formula. For mathematicians, it is one instance of can be understood as one instance of the Sanoff theorem in the theory of large deviations. But to the eyes of an engineer, it is important. If I know the statistical distribution and I can compute really the value and start doing computation. It's a fundamental step before the applications. And also for Boltzmann, it was important because he would be able to work with this and make predictions, not just agitating hands and saying, because of this and that reason, entropy should increase, then doing a proof, a mathematical proof. And that may have been the single most important contribution of Boltzmann. Using this and the theories of partial differential equations to prove the big theorem of increase of entropy. So partial differential equations, this, let's say, is for people who have never heard about them to appreciate their beauty. Partial differential equations are equations describing the evolution of various phenomena around us or in the world of mathematics. They have been used to describe the evolution of gases, like the Boltzmann equation, evolution of galaxies, like the Vlasov equation, evolutions of atoms, like the Schrödinger equation, evolutions of fluids, like the Euler and Navier-Stokes equations, which are used all the time to predict the weather or to make special effects in the Hollywood studios, or equations of reaction diffusion, like Alan Turing tried to use to do some morphogenesis. In the case of Boltzmann, this here is the equation that he used. Nowadays, it's called the Boltzmann equation, even though it was essentially first written down by Maxwell. But you know, Maxwell and Boltzmann were playing ping pong with these concepts, doing a scientific revolution. This equation allows you to predict very finely what will be the evolution of the statistics in the gas. Now, remember, I told you the evolution of one particle is unpredictable. But the evolution of the statistics is predictable. It's exactly the same conceptually as when I said one coin that you toss, you don't know if it will be head or tail. But if you toss it 1 million times, you know that it will be like 50%, 50%. Also, to pursue the analogy with demography is the same as to say that you never can know if this guy will marry and have children or die early at a young age and whatever. But if you look at the size of the country, you can very well predict what will be the birth rate, the death rate, what will be the evolution of the population over the next 10 years, taking into account the demographic parameters. Exactly the same. And Boltzmann combined this equation with the formula of the entropy, which I showed before, to prove his big theorem, the so-called H theorem of Boltzmann. Entropy goes up. It was known in thermodynamics that entropy had a tendency to always go up for an isolated conservative system. But this was a law that was observed through experiments. Boltzmann transformed it into a theorem, at least for a gas, and this was a giant conceptual leap. He, for instance, computed this variation of entropy using the equation, the formula, and showed that the variation is always non-negative, so it always goes up for a gas which is isolated. This was a huge progress and also opened up so many questions. First question, how long will it go up? Up to where will it go up? And you can convince yourself that it will go for the maximum entropy. That's a huge prediction. Allows you to compute what will be the final state of a gas. Then it's a mathematical problem. Ask which is the distribution which has the maximum entropy. You sit down, write the calculation, and guess what? We find the law of errors again. It was not summoned here, but it's the same law that was describing the fluctuations of the head and tail tossing that is describing also the final state of the gas in terms of the velocity distribution. Now, mathematicians love this when the same object appears in various contexts, and even more when it's not clear that there is a connection. It turned out there was deep connection. Now, this gives solution of another problem. Well, where the gas does go, it will go to this state. But immediately, it raises a number of other questions, like how fast will it go there? How fast will the entropy increase? How fast will I approach the state of Gaussian equilibrium, Gaussian distribution? This is where I worked for quite some time during my PhD. In particular, on the conjecture formulated by the late Carlo Cerciniani, like an inequality relating the entropy, the value of the entropy, and the value of the increase of entropy. Like if the entropy is low, then the production should be very large, so that it will immediately go close to the value of maximum entropy. And this is the first work that I am really proud of. I was 24 years old, where this was collaboration with Giuseppe Toscani, a start of a solution of this conjecture, a partial solution. And this was the start of many works on the theme, which had been explored before by Laurent Devillette, Eric Carlen, and others, on the themes, how fast does the entropy increase, how fast does the gas become Gaussian. It's inspired by physics, but it's a mathematical problem. And in fact, this is the last time I'm showing the grave of Boltzmann. Boltzmann tragically committed suicide in 1906, not sure that his idea would ever be checked and that entropy and would have real applications in physics. Not only did it have application in physics, but it also inspired mathematicians like Mark Katz, who stated that the book of Boltzmann was one of the greatest ever written in exact sciences. But also engineers, people developing theory of communication like Shannon, but also people building cars and building space shuttles and whatever, and who want to understand how the gas in the device will behave. Let's continue in this train of thoughts and note that entropy was an extremely successful concept from the point that it was made a mathematical concept, because then it could go in a number of different situations. And on this slide that I will very quickly browse, I mentioned a number of spectacular applications of entropy in mathematics. Entropy was developed as a tool to understand physical problems, but then it became applicable to problems in mathematics also. It was part, of course, of all the studies on gas theory. Here I put some of the influential names in the use of entropy to understand the behavior of the gas, not just controlling equilibrium, but also controlling if the gas doesn't blow up and so on. Played a key role in the study of fluid mechanics, information theory I mentioned, quantitative laws of errors. Now, by a twist of the history, the entropy was used to give another proof of the theorem of Laplace about the fact that you have Gaussian fluctuation for probabilistic experiments. But also it was important in what may be Nash's most famous mathematical result for people in analysis, regularization for non-smooth diffusion equations. But also it was important for Gregory Perelman when he proved the Poincaré conjecture. He did use some entropy. Also it is important when you want to understand how to establish the laws of the fluids from microscopic models. Also it played a key role, the entropy of Boltzmann, in a work by Dan Voiculescu in non-commutative geometry, which has nothing to do with physics or so remotely that you really need a lot of explanations to see the connection to physics, and so on. So once entropy was formalized as a mathematical concept by Boltzmann, it had many applications also in mathematics, showing that physics also irrigates mathematics. Let me then slowly proceed, or quickly proceed because I am late, to another part in which entropy was important and in which I played a role and which was evoked by Robert McCann. And for this, I will first evoke the work of Leonid Kantorovich, a fantastic Russian scientist of the 20th century. Kantorovich alone is also a symbol of mathematics in all its diversity, from very pure to very applied, working on such theoretical subjects as partly ordered spaces and on such practical subjects on what is the best way to devise the recipe for taxi fare. And he was a pioneer in the numeric approximation and calculators. His best work still is in mathematical economy. His masterpiece, The Best Uses of Economic Resources, owed him the Nobel Prize in Economics in 1975, making him one of the rare mathematicians to have obtained the Nobel Prize after all. Leonid Kantorovich is one of the heroes in an amazing novel, which I recommend, Red Plenty by Francis Burford, showing the rise and fall of the Soviet economy from the point of view of the concept of mathematical planification, where the heroes in the book are people, some of them real, some of them imaginary, but in there, the main hero is the idea of mathematical planification from the basic ideas of Kantorovich to the point where the mathematical planification comes in contradiction with the interests of people and ends out in wreckage. Now, Kantorovich had his life transformed by plywood. Yeah, plywood is not something very sexy a priori. It's a combination of woods, which may be hard and soft wood that you press together, and there you obtain some material. By the way, it is credited to the father of Nobel. And one day, these people from the plywood industry, they came to see Kantorovich, who was very young but already the head of his department, having obtained his professor position at age 22. And they asked Kantorovich for help. Like, we are making this plywood, there are so many possibilities. We take the softwood from this forest, the hardwood from that forest, transport the wood here. We have a big machine able to handle so much of hardwood, a small machine handling this, and so on. And there are so many possibilities that we don't know which is the best for increasing our production. Kantorovich thought about it and first had no idea about how to help them. But then he realized this could be recast as so-called linear programming problem, which is one in which you have a bunch of inequalities in which the unknowns enter in a linear way, not nonlinear, and you try to optimize a quantity which also is linear. And this is a field in which you can make exercises. I remember vividly how I was happy in high school when our teacher would give us problems of this kind. And when you have 2 or 3 or 4 inequalities, you make a graphic resolution. But when you have 1,000 inequalities, don't think of it. Nowadays, in the industry, sometimes they have 100,000 such constraints to satisfy at the same time. And of course, to do this, then you need a mathematical theory. And Kantorovich was one of the first to start this mathematical theory. By doing so, Kantorovich realized he could solve mathematical problems from the past. In particular, a problem which had been devised by Gaspard Monge at the end of the 18th century, the so-called optimal allocation problem. Imagine you have material produced at points x1, x2, x3, x4 that you want to transfer to final destinations, y1, y2, y3, y4. It doesn't matter which goes where, except that you want the total amount of energy spent to be as small as possible. So you want ideally that the y destination is as close as possible to the x starting point. But then it's a global problem, and you have to find which is the best way to match the starting points to the final points. And Kantorovich, for instance, realized that you can transform this problem in another problem. Instead of minimizing the sum of the cost, the energy that you spend to go from the start to the end, you hire somebody to do the transport in your place. And with that somebody, you will together decide what will be the price at which he will buy the material from you at the starting positions and selling back to you at the final destination. And because you want to make sure that this guy is making you a good offer, you will impose that the difference of prices is never more than the price of that energy that is spent to go from the start point to the final point. And if you look at this, this corresponds exactly to the profit that the somebody is doing. And what Kantorowicz shows is that there is a relation between the best possible transport and the best profit that will be made by the other guy. You see here with these few explanations how it's related to problem in economy. Now you can believe that Kantorowicz was working on problems with application in economy. You can also understand, by the way, that Kantorowicz was extremely brave, trying to make a theory about prices and something here that looks like a profit in Soviet Russia at the time was literally trying to get to Gulag or to be executed. For less than that, you could well be executed. It was strictly forbidden to talk in public about the Kantorowicz theorems, and Kantorowicz was spared certainly because he was useful to other projects, like atomic bomb. Shows you also another thing about mathematics that we did not evoke so far. It can be very embarrassing because you have a theorem, it can contradict an ideology, it can contradict something people are hammering, and because it's a theorem, there is nothing you can do against it, except kill the author. Nowadays, the Kantorowicz theory is extremely popular. Not only do we talk about it in public, but it is in many courses in economics. I gathered from internet some examples from tutorial in which linear programming and the Kantorowicz theory is applied to all these various problems. All of them you can put in the form of a linear programming problem. And you even have softwares that can do this automatically. Still, it's important to know about the mathematical theory to see in which situation to use which kind of program. Now, in this talk, we saw the adventures of three great scientists with different times, different problems, different methods. I started talking about geometry. It was the occasion to say a few reminders about mathematics in general. Then we moved to the core of the subject with entropy and Boltzmann. And then I started this digression about Kantorowicz and the problem of minimal cost. It's on purpose because, in fact, these three stories are strongly connected. And I was lucky enough to be part of a group of people, some of them in the audience also, who discovered at the turn of the past century that there was this close connection between these three theories, close connection that nobody expected. How this came is not because one of us at some point started to think and say, I think there is a connection. It came by randomness and because at some point there were people meeting and discussing about this and that. Let me take this opportunity to recall that, this I stole from a cool blog, science is not done like this. Like you have a challenge, you search, you work hard, and find the answer and get the Nobel Prize. It is more something like this, in which you do mistakes, do science, you have instrument that breaks, for instance, and what the hell, not going quite as expected, amazing results, which turn out to be crap, and you wonder what the hell is going on, thinking, that's funny, makes no sense, yes, oh, this makes sense, oh, they figured this out 50 years ago, okay, back and then, okay. This will look familiar to anybody who has done research. But it would be even closer to the truth if you would consider this as one ring and think of the stories of many people like rings that are bound together, because we are all doing this for ourselves, but interacting also with other people. In this subject, for me, probably the two most important encounters. First one was Felix Otto. He's here, must be very embarrassed to see himself here. And after we met in France in 98, I came to visit here in Santa Barbara in 99. And this was to work on problems precisely relating the three stories: the entropy, the curvature, the minimal cost. And another key encounter in this subject was with John Lott a few years later in Berkeley. This is the beautiful sunny Berkeley campus, in which people are always happy. And this is the famously ugly Evans building, the building of mathematicians. And when you arrive there, you see that the building is very inconvenient because it is organized in layers so that you never meet anybody from the layers which are not your layer, and there is no and all the people, they are so very busy because it's big Berkeley University with famous busy people. I was visiting there in 2004 as a visiting professor of the Miller Institute, and I was very annoyed. You know, I did not have much duty to do. It was very good conditions. No teaching, no obligations for research, no administration, only one lunch to attend every week with the other fellows, and for this I was paid 3 times my French salary. And still, I was embarrassed because I knew there were all these great mathematicians, but how to interact with them? I don't meet them spontaneously. Important of a research building is that spontaneously you should meet the other people. And there came John Lott. He was invited as a guest of Mathematical Sciences Research Institute, just above the hill. So he was, as a guest, he had much more time, and then he arrived in my office and said, "Oh, I read your paper with Felix Otto. We're going to apply this to develop a new theory of non-Euclidean geometry," and so on. And this was an important starting point for me because there I started to really go into the non-Euclidean geometry. So the one picture that will explain the connection and what we were doing with Felix, what we are doing with John, what also came out from the works of the various people, including Robert McCann, who was presenting me, and Carl Theodor Strom, who may be in the audience, who is participating in the symposium anyway. I will summarize by this, called lazy gas experiment. I will tell you that it will make the bridge between the three fields that I discussed, and starting from there, you have a better understanding of each of the fields, a better understanding of the optimal transport problem, a better understanding of the curvature, a better understanding of the entropy. And this is really why it's precious. In particular, problems which were set in terms of geometry, we were able to solve in terms of entropy. And to this day, nobody has found how to solve these problems purely in terms of geometry. But through the connection, we found a way to get these. So here is the connection. Imagine I have this gas which at initial time has a certain configuration, a certain statistical configuration. Like there is a part of high density, a part of low density, whatever. And this gas I order to go in another configuration after time equals 1, say 1 minute. So the gas has 1 minute to go from this state to that state. It's not like the Boltzmann problem. In the Boltzmann problem, I put the gas in the box and I let it free to do whatever it wants. Here, I impose the final condition. The gas will obey, but being lazy, the gas will choose a way to do this which spends the least amount of energy. And while the gas is doing this, we are measuring the entropy in the sense of Boltzmann all along. If the curve is always like this, the curve of entropy as a function of time, then it will mean that this is a positively curved space. So you see here how the various concepts are related. The geometry with the curvature, the economy in the sense that the transport should cause the least amount of energy, and also the statistics, because all you impose is the statistics of the gas, not the individual positions of the molecules. How can we understand that there is a connection? Here is an idea. If it is positive curvature, then the geodesics, the trajectories of the gas, will typically first spread and then converge. Remember, on the sphere, the lines were emanating from a point, separating, and then meeting again. Here it's a bit the same, right? Separates and then meets again in the end. But if it separates, if we look at the gas, because the particles tend to go apart, the gas will spread. And remember the experiment about the box and the gas spreading in the box going to higher entropy. Here the gas is more spread in the middle. So this should correspond intuitively to a high entropy. It's more disordered than if the gas is concentrated. And so that's the idea. Positive curvature, so more space in between for spreading, so more entropy. This is the basic idea. Then from this, a lot of work to make this rigorous, to quantify this, to draw the implication and so on. And in fact, this was one of the key concepts, key tools behind within a book which I wrote, a reference book which I wrote on the subject, which is a thick 1,000-page book. So I will not say more and just mention that, as I said, some problems, for instance, which were formulated in terms of curvature and looked like just problems of curvature, were solved by using this and introducing artificially like a gas and seeing how it evolves and making the reasoning on that. Also that many people jumped in to continue our work. It's very difficult for me to keep up actually with the recent research in this because there are so many. If I wanted to, my book appeared in 2009, if I wanted to continue the book to take into account the progress made in these past 5 years on this subject and do it with the same degree of precision that I did before, it would double the size of the book, roughly speaking. And this shows also, in the end, that's important when you do some work. It's not so important to have the final word. It's important to start the things that many people will be able to continue. Yes, this was the book. Also, a final comment. These works came through encounters, and actually it was talked about my work by Robert, but in fact it's not my work. It's always collective work. And but Robert did a good work of mentioning my collaborators. 3/4 of my papers have been made in collaboration with people from at least 10 different countries. And it always started with encounters and random ideas. We know in mathematics so well that these random encounters are important that we have institutions devoted to these encounters. And the institute that I run, Institut Poincaré, is precisely devoted to this, so that hundreds of people every year will convene there and there will be new ideas coming up and new mathematics. And to some extent also, this is the role of the Fields Institute, to foster these interactions between people and make it so possible that people will bump into each other and emit new ideas, and the new things which will be started, nobody has an idea a priori. That will be all. Thank you very much. And you see that's the idea of using the entropy of human encounters to generate the mathematics.
Thank you. Thank you very much, Cédric. It's a very lovely talk, and it left us with a very warm feeling for the concept of entropy. We're now going to just finish up. Merrick Gertler, who's the president of the University of Toronto, sent us a message electronically using a GPS. No, not relativistic effects, but using Shannon. That says, unfortunately, it's a convocation this week, this evening, and unfortunately he could not come. But we have a replacement to give us a final word at the end of our evening. So he will be represented by Dr. Peter Lewis, who is the Vice President of Research of the University of Toronto, who graciously will step in without any time for preparation, except writing notes on his knee during the talk, and serve to close our ceremony. So, thank you very much. And here's Dr. Lewis. Thank you very much.
So thank you. As John indicated, Merrick was really double booked this evening, and it's my pleasure to close this lecture. It's fascinating to me. I'm actually a biochemist like Mario, and entropy actually plays a major role in determining how proteins fold up in your body and organize cells. So this lecture on the theory of entropy has been quite an eye-opener for me. So thank you all tonight, and I wish you all the best from the University of Toronto for the rest of your symposium. Thank you.